chat. Okay, we are going to talk about counting. So in bahasa Indonesia we call this menghitung. So how do we count things? So things that we are going to count, well, counting basically also revert to do something that is discrete. So when you are doing counting, basically you're not calculating or computing. When you're doing counting, well, there is a sense that what you're doing is something with integer. So counting basically means that 1, 2, 3, 4, 5, and so forth. So counting is also called combinatorics. So another name for this in mathematics is called combinatorics. And this is actually a very large topic in mathematics. And if you go to the Department of Mathematics, you can even encounter a specific course, an even advanced course on combinatoric. Yeah. Okay. Now, counting again has something to do with sequence. You see, actually, the second half of the semester of discrete math deals with sequence. So sequence basically is a very powerful abstraction. By using sequence, you can do a lot of things. Now, if you remember in the beginning, we talked about summation and product. At that time, we basically sums or add together all of the components of a sequence. Okay, and then afterward we talk about recurrence, and in recurrences you basically represent precisely a sequence. You can have a precise way of presenting a sequence. Now we are talking about counting. What is it? Well, we will see that in counting it's easier to be done when you do it in sequence. So this is the main what do you call this? The main strategy that we are going to use. We are going to convert all of our counting problem to sequence. So every time you find a particular problem in counting, you try to bring that problem to sequence. I hope this will be clearer later on. So let's start then. Look at this list of numbers. This is a very large number, and there are 90 numbers there, and they are very large numbers. Each of them is a very large number. Yeah, I think it consists of almost 20 digits. Each one of them can be up to 20 digits. So this is a very large number. But then I can claim that there must be at least 2 different subsets of these 90 numbers that exactly have the same sums. Yeah? Think about it again. So there must be at least 2 subsets, 2 different subsets. So I don't know the subsets. The subsets can be, take 2 of them, okay, take 3 of them, take 4 of them, and so forth. In one subset, you may take 3 of them. In another subset, you may take 4 or 5 or 10. I don't know. Yeah, we don't really know. It is not. I mean, the claim is basically not constructive in the sense that you cannot show me the number. But then this is basically a claim, and I will later on prove. The proof is not constructive, but I can prove that there must be at least 2 subsets, 2 different subsets of these 90 numbers that have, so these 2 subsets have the same sums, exactly the same sums. I mean, how can I make such claims? How do I prove it? This is what we are going to see in counting. Yeah? Counting is really important in computer science. There are many things that you have to do in computer science that deals with counting. For example, when we want to predict or we want to compute the time, computation time, or the storage requirement to solve a particular computational problem, most of the time we deal with counting in this problem. So we will resort to counting, and then by using this counting, we will say something to do with the computation time or the storage requirement of the algorithm. Okay. Another is that probability, the basis of probability is actually counting, especially when you are doing something called frequency probability. Yeah, probabilistic frequency. So the probability that relies on the frequency. I think you will take a probability later in the next semester. Yeah. So and then you will see later on that there we use counting a lot. And then there are also two proving technique. You have seen in the starting, in the beginning of the semester, there are lots of ways to prove something, and you haven't seen these two things. The first one is called pigeonhole principle, and the second one is called combinatorial proof. And these two ways of doing proof are actually relies on counting. Yeah, actually relies on counting. Okay, let's continue. Then, this is what I said before about the most important strategy of doing counting. So this is the core of the counting, and you have to basically understand this, and be able to use it. So this is really important to understand. So the main technique in counting, be it a simple counting problem up to the most complex counting problem, yeah, is usually by using this technique. Namely, to count something, you count something else. Yeah? So listen to that. To count something, you count something else. Because what? Because if you count that something right away, it may be really complex and difficult. But when you transform that counting problem to another way of seeing it, it will become clearer and simpler. Formally, every counting problem is basically is a problem of determining the size of a set. Look at this. Yeah. So that means everything that we are going to deal with, we will convert it later on to sets. So every counting problems, in the essence of every counting problems, is the problem of determining the size of a particular set. And you know already about this set. So the size or the cardinality of a set S is the number of elements inside of that set. Of course, this set can be infinitely large. In this case, that we are not going to count it. Counting only deals with finitely large set. So the cardinality or the size of the set is denoted by these symbols. So if S is the set, then this is basically the cardinality or the size of the set. So back again to the main technique that I mentioned before, we will determine the size of a set S by determining determining the size of another set T. Of course, these set S and T are not independent of each other. There must be some connection between them. And then this is what we are going to talk about in this lecture, basically. So how to create another set, namely set T, from a particular set S. So there must be a correspondence between them. When you are doing counting directly on S, you have problem. But then later on, when you are doing counting on set T, then everything will become simpler. Okay? So let's continue. So how do we make this connection between these two sets. We have already also covered this topic before. I think in the well, before the midterm exam, there is a tool, a mathematical tool for that, namely relation. Relation basically relates or creates a mapping between two sets, between the elements of two sets. And by looking at the relation, its characteristics, and so forth, we will be able to do a lot of things. Okay, let's continue. So this is the main idea, like I said, the main technique. Yeah. So we talk about the bijection rule, and this is the first rule that we're going to see, and this is actually the main technique that I mentioned before. So the main technique is called the bijection rule. What is the bijection rule? The bijection rule is easy. If you can create a bijection is a function from A to B. A bijection is a one-to-one correspondence. So that means for each element in A, there must be one and only one element in B. So the mapping basically creates a one-to-one correspondence. Then the number of elements or the size or the cardinality of A must be the same as the cardinality of B. So this is easy. I mean, this looks like a trivial rule, but this is a very important rule. Yeah. So let me repeat again. So if you can create a bijection, if you can find a bijection is a function from A to B. So any function at all, any bijection at all from A to B, then the size of B must be the same as the size of B. I will demonstrate this by using an example. Let's look at this example. Assume, for example, that the set A contains all possible ways to select a dozen of donuts, if there are 5 flavors. So think about this. So there are 5 flavors. You can go to Dunkin' Donuts, for example, and they have 5 flavors, and you are going to select. You're going to create a configuration of a dozen of donuts. So how many ways do you have to create this dozen of donuts out of these 5 flavors? And the second one, look at this. The second one is a set B. The set B is all binary strings, all 16 bits binary string with exactly 4 ones. So you can imagine there is a 16-bit binary string, and this 16-bit binary string has exactly 4 ones. So the rest of the bits, namely the other 12 bits, are basically 0, because this is a binary string. Yeah, look at these two sets. They are sets. The first one is all of the way to select a dozen of donuts out of 5 flavors, and the second one, all of the binary string. So the element of the first one is ways. So this is the first way, the second way, the third way, and so forth, while the elements of B's are binary string. Okay, now let me show you. Let us pay our close attention first to set A. Yeah, so how does it look like? For example, let's look at A. So assume that we have 5 flavors, and the 5 flavors is like this: the chocolate, lemon, vanilla, mint, and normal. Normal means that there is no flavor. It's just a normal donuts. So this is one of the elements of A. Look at this. One. Let's look at one element of A. Yeah, one. Let me take one particular element of A. The element of A can look like this. So what is the interpretation of this one? The interpretation is like this. There are 2 chocolate donut, 0, because there is no, yeah, there is no lemon. There is no donut with lemon flavor. There are 6 vanilla, 2 mint, and then 2 normal. Yeah. So the zero here, you see here, the zero here are basically represent a donut. So there are 1, 2, 3, 5, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, yeah, there are 12 donuts in total. So if you look at this look like one element of the set A. And of course, the element of sets A can be any configuration that you can think of. There are many other configurations. Think about it. The first configuration, for example, all of the 12 donuts consist of just chocolate flavor. That means that there are 12 donuts here, and then the rest will be 0. But there are many other ways. Think about it. Then the problem is right now, how many ways are there? Yeah? So a donut is represented by a 0, and you see there is a gap here. There's a gap between one flavor to the other. What if instead of the gap here, I will put a 1 there, and the 1 will basically represent the gap. Yeah. So the gap will be 1. So if you look at this, then there will be 2 chocolate, and then we have the gap, and then 0 lemon and the gap, and then 6 vanilla and the gap, and so forth. So this is, well, this here is just another way, another representation of this one. Okay? You see the point right now. Okay, let me continue. Okay, now, but then when you look at this example here, well, this is actually a binary string, and the length of this binary string is 16 bits, and there are exactly 4 ones there. Yeah, there are exactly 4 ones. No matter how you create this donut, how many donuts do you have for each flavor, the gap must always be there, and the gap there can always be 4 gaps, and because each of the gaps is represented by 1, so this is exactly a binary string, a 16-bit binary string with 4 ones. So you see, I just create a correspondence from A to B. So my argument basically says that, well, for every element in A, there must be a corresponding element in B because of the way I created. And you can see the argument there. Yeah. So what I have just did, what have I just done actually? What I just did is just create a bijection. I just create a function. This function, of course, is not a straightforward function. This function is a quite complicated function, but you have the idea of this function. The function basically says that for one configuration of the donuts, then I will add a gap in between, and if a donut is represented by 0, and then the other one can be read as just, yeah, so the resulting representation can be read, can be considered as a sequence of bits, a binary string. You see, this function, I mean, it is not easy actually to represent this function, but you can tell the story of this function. Yeah. Now, because this is a bijection, then this theorem applies. This theorem basically says that the number of elements in A must be the same as the number of elements in B. Okay, let's continue. Now, I'm going to tell you further about the bijection, the function. So we map a dozen of donuts that contains C number of chocolate, L number of lemon, V number of vanilla, M number of mints, and B number of normals. That means that this will look like this. There are as many of C with the chocolate, L with the lemon flavor, and then V numbers of vanilla and so forth. Yeah, so this is it. So this is basically a dozen of donuts with 5 flavors. You map this. You map this into a string, a binary string that is always of 16-bit length, and there are exactly 4 ones inside of this. And because of this, of course, this set of binary strings, the contents of 16-bit and 4 ones, are elements of B. This mapping is a bijection. Because what? Because for every binary string, yeah, then you can, you can look at this in a different way. For every configuration of donut, there must be one particular string. And also for each string, you can think of, imagine, I can give you any 16-digit string, basically. Take any 16-digit string that contains 4 ones, and then you see it must correspond to one particular configuration of donuts. Therefore, the number of elements inside of A must be exactly equal to the number of elements inside of B. You see? So this is the first rule. And this rule is the most important one. This allows you basically to convert a problem, a counting problem, to another counting problem. All you have to do is finding a bijection between them. Once you create a bijection, then there must be, both of them are basically the same counting problem. Okay. And then what does it have to do with sequence then? Well, the bijection rule allows us to count something by counting something else. For example, instead of, if I ask you, for example, in this one, how many ways are there to select a dozen of donuts with 5 flavors? This is actually a very complicated problem. It is not easy for us to grasp this. It is not easy for us to imagine this. Yeah? And to put it in our mind, this is something really complicated. But then later on, we will see that if what I ask instead of is B, namely to find how many ways, how many the binary strings are there, how many 16-bit binary strings are there, it exactly has 4 ones, you will see that it's easier actually to solve this. It is easier to solve B. This is basically the first rule. The first rule allows us to count something by counting something else. So our general strategy is to really master how to count a couple of things, and then use this to count any other thing. So really master to counting something, a couple of things that we will see basically based on rules. There are around 12 rules that we are going to see in this lecture, and then use this to count any other problem. Yeah? So what do? We are going to learn, we are going to master how to count sequence. So this is basically the secret. Yeah? So what we are going to do is we are going to really master, to look at the detail of how to count sequences. So any sequence that we are given to us, we are going to find a way to count them. Now, then if you are given a particular problem, a particular counting problem, all you need to do then think about how to convert this problem to a sequence. And then once you have the sequence, you have the arsenal, you have the tool to manipulate this. Yeah? So then you can solve this easily. So if you want to determine the size of set T, We try to find a bijection from T to another set S, and then, well, S is easier for us to solve, then, yeah, then if once you find this bijection, if you know how many elements are there in S, then this, I mean, the same number are in T. Okay? Now, later on, we will see a lot of examples that basically to highlight this idea. Okay, let's continue. Let's look at the second rule. The second rule is called the summation rule. Yeah, the summation rule. Look at this theorem. If A1, A2, up to AN are all disjoint sets, so there is a condition there. It must be they must be disjoint sets. What does it mean by disjoint? Disjoint means that any two of them do not have any intersection. Any two of them have no common elements. So that means that if there are n of them, none of them whatsoever. I mean, any two of them, they don't have any common elements. Then if this is the case, then the number of elements inside of A1, union A2, union, and so forth until the union AN must be equal to the number of elements in A1 plus the number of elements in A2, and so on, plus the number of elements in AN. So this is easy. So if you know that they are disjoint, then union is converted into summation. That's why we call this the summation rule. Okay? Now, this is the first one. This is the second rule, basically. I will not show you an example of this. We'll collect a couple of rules first, then show you an example. But this is easy. Yeah, this actually looks like trivial. You may say right now, well, this actually looks like a trivial thing. Why do we have to learn about this? But this is important. Yeah, this is important because in here we are dealing with cardinality, the size of the sets. Yeah, and each one of these sets may contains also sequence. So that's basically the idea. If we go back, we are going to convert this into sequence. Okay. Now let's look. Then let's continue with the third rule. The third rule is called the product rule. But before we continue with the product rule, I want to remind you of something. If A1, A2, up to AN are all sets, there is no condition whatsoever, then A1 times A2 times and so on until AN are are sets of sequence. Yeah? Sets of sequence where the first element, the first term, is taken from this one, from A1. The second term is taken from A2, and so on until the nth term inside of this sequence is taken from AN. Yeah? So you know, I mean, you're supposed to have seen this in before the midterm exam. So this is basically how to create the product of several sets. What is the product of several sets? Yeah. Now, if you have already known this, then we have the third rule, namely the product rule. The product rule says that if A1, A2 until AN are all sets without conditions, then the number of elements, the cardinality, the size of A1 product, so times A2 times and so on until N is just equal to the product of each cardinality. So the size of A1 multiplied by the size of A2 and so on multiplied by the size of N. So this is easy. That the times here, the product is converted to multiplication. Yeah? So let me show you an example. An example out of these two rules. Yeah. So how many valid passwords there are if the length of the password, if you are allowed to create a password and this password must be between 6 and 8 symbols, the first symbol must be a letter, and this letter can be capital or not, and the rest of the symbol can be a letter or a number. So alphanumeric basically. So the first symbol must be an alphabet, can be capital or small, and the rest of the symbols, the second, the third, and so forth, are alphanumerics. So this is what we mean by counting. How many password can be? If you know how many password there are in this one, then you can imagine actually of how we can try to do brute force basically, yeah, to 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 try to guess. If you want to guess somebody else's password, how many guess do you have? How many how many trial do you have to do to find this particular uh, to to find the password? Okay. So how many passwords there are? So let's see. These password things here are ordinary problems, real life problems. If you try to answer this right away, it is not actually easy to answer that. But we will try to convert this problem into a sequence problem. You see, so our first step must always be try to bring this problem into a sequence problem. So how do we do this? Let's think about it. We define first these two sets. The first set is called, this one is alphabet. Yeah, this is the alphabet. And this one is the alphanumeric. So this one is basically a set that contains a, small b, and so on until small z, capital A until capital Z. How many are there inside of this set? Well, 26 times 2, yeah, 26 times 2, 52. So there are 52 elements inside of P. And then we have B, another set. These sets, yeah, contains small a until small z, capital A until capital Z, and in addition to this, the numeric from 0, 1, 2, 3 until 9. So how many elements are there inside of B? There are 52 plus 10, 62. Yeah? So this is basically our building block, because when we are creating the password, we create this out of these elements. Okay? Now then, what can we do? So this is just the solution to our problem. Look at this. So the password that we are creating, look at it, we are talking about the password right now. We are not talking yet about the number of the password. We are talking about the password. So the password that we create can be 6 digits long, 6 symbols long. And if it is a 6 symbols so long, then this must be P multiplied by, or product. If you create the product of the sets, P product B, product B, product B, product B, and so forth 5 times, because the first one must be the alphabetic one, and then the second symbols up to the 6 symbols must be an alphanumeric one, can be an alphanumeric one. So this set basically contains P multiplied by B to the power of 5. So this is the 6 symbols one. This is the 7 symbols one. This is the 8 symbols one. You see? So you see, this is easy. So what I have just created here, basically, I just create a set that contains all possible symbols, all possible password, I mean. I just create right now a set that contains all possible passwords. You see, This is a set. This is also a set. And b to the power of 5 is easy. B to the power of 5 is just b multiplied by b multiplied by b multiplied by b multiplied by b. And you know how to multiply sets. Okay. Now, once we know this set, next thing that we have to do is just to count the number of elements inside of this set. How many elements are there inside of this set? Well, this is easy. We just use the last two theorems that we saw. So the number of elements or the cardinality of this set is equal to, first, look at this. We look first at the union, because this set is disjoint from this set and disjoint also from this set. They must be disjoint because this just contains six symbols. This is 7 symbol and this is 8 symbol. It must be disjoint. Yeah. Then this union here becomes summation. Yeah. So from summation rule we have this one. So the cardinality of p multiplied by b to the power of 5 plus the cardinality of p multiplied by b to the power of 6 and so forth. Okay. And then the next one. The next one says if we have this set p multiplied by b to the power of 5, then the number of elements is there is just the multiplication. This is from the multiplication rule or the product rule. So from the product rule, this will be equal to the cardinality of p multiplied by the cardinality of b to the power of 5 and so forth, plus the cardinality of p multiplied by the cardinality of b to the power of 6 plus the cardinality of p multiplied by the cardinality of b to the power of 7. How many are there in p? 52. In b, 62 to the power of 5. What does it mean by 62 to the power of 5? This is just equal to b multiplied by b 5 times. So this must be 62 multiplied by 62 and so forth until 5 times. So you have these numbers of elements. And if you sum them all together, this is around 1.8 multiplied by 10 to the power of 14. The power of 12 is trillion. And the power of 12 is just a trillion one. So these must be around 180 trillion passwords. 180 trillion possibilities are actually very small right now if you are dealing with a computer. If you just use a password of this length, it is not actually take a long time for a computer to try to guess, to try each one of them. Yeah. So that means that it is not actually a good idea to create a password with just this complexity. So how do you create a better password? Well, I can create a better password. The first way to do that, if I add the length, so the longer your password, the better it is. Or if you give more variety to these sets here. This just contains 52 elements. This one contains 62 elements. But if you add other symbols, there are a lot of symbols, the rest of the symbols, these can be enlarged. And if you enlarge this, the number of possibility becomes also very, very large. Yeah? So, okay, let's continue.